Hello and welcome to this video on Python standard library. So a special welcome to those who are new to the channel. If you are new to the channel, make sure that you subscribe to the channel and press the bell icon so that you can get notified about the upcoming videos on this channel on Python programming. So we will continue our read through of standard library. So in this video we will study list, tuple and range sequence types. So without further ado, let's get started. There are three basic sequence types: list, tuples, and range objects. Additional sequence types tailored for processing of binary data and text strings are described in dedicated sections. So we start with common sequence operations. The operations in the following table are supported by most sequence types, both mutable and immutable. The collections.abc.sequence ABC is provided to make it easier to correctly implement these operations on custom sequence types. This table lists the sequence operations sorted in ascending priority. In the table, S and T are sequences of the same type. N, I, J, and K are integers. X is an arbitrary object that meets any type and value restrictions imposed by S. The in and not in operations have the same priorities as the comparison operations. The plus and star, that is concatenation and repetition operations, have the same priority as the corresponding numeric operations. So let me fire up the editor and open our file. And we open our file, the Python one, this one. Okay, and let's go to our editor, Python 3 programming, and we will run this. So first operation is X and S. True if the item of S is equal to X, else false. So for example, let's create a list 1, 2, 3, and we print 2 in L. Okay, let's see what it gives us. So we say Python lib12.py, it is true. So similarly for strings also, even though this is not string section, but strings also satisfy this property. ABCD print A in S. So that also is true. Now the second is X not in S. False if an item of S is equal to X, else true. So you can say that 4 not in L. So it will become, did I not say? Yeah, this is true. 4 is not in L. So it becomes true. S plus T. This is concatenation of S and T. So let's say we create another one, 4, 5, 6. Okay. And we print L plus M. Or we can do this way. L is equal to L plus M. And what we do after that is we print L, M, and N, all of them. So 1, 2, 3, and 4, 5, 6 will get concatenated. So this is L, this is M, and this is L plus M. So you see that original lists are not modified in this case. Okay. Similarly, you can say S is equal to ABCD, T is equal to DEF, and you can say U is equal to S plus T. And let's see what happens here. Since strings are mutable types, there is no way they will be modified. Okay, so we run this. So ABCD DEF, ABCD DEF. So we have seen the concatenation. Then we have repetition, S n times or n s times. So we remove this. We say print 2 times L comma L into 3 times. So L should be printed a total of 5 times. So we have twice the L and 3 times the L. This will also work on string types. Item of S at index 0. So this we have seen. For example, you can say L0, or in case of a string ABCD, we can say S0. So it will give 1 and A. Yeah, it gives 1 and A. Next we have slice of S from I to J. Note that in this case I will be included and J will be excluded. Okay, so we see this L0 colon 2. So 0 and 1, that is 1 and 2 should be printed. 0 colon 2, so A and B should be printed. Or we make it 3, so first 3 should be printed. So 1, 2 and ABC. Next we have slice of S from I to J with the step K. So that is similar, you can experiment with this. We have len S, which gives us length of the sequence. It is determined by the underscore underscore len underscore underscore function. We have min and max. So if you want, you can invoke min max, min of L, and say max of S. Okay, let's see what this gives us. So this will not work. Oh, sorry, x will not work. This should work. So 1 and D are given. Minimum of 1 to 3 is 1 and maximum of ABCD is D. Then we have S index, index of first occurrence of X in S. So, and you can further give it a slice also. And then we have count function, S dot count, total number of occurrences of X in S. So sequences of the same type also support comparisons. In particular, tuples and lists are compared lexicographically by comparing corresponding elements. This means that to compare equal, every element must compare equal and two sequences must be of the same type and have the same length. So comparisons has a full length discussion here. You can go through this. This is not a big one. We will go through it. Okay. It's a small, no, it's a big one. Value comparisons on one. So I'll let you read this, and maybe if you have questions, you can come back and ask in the comment box. If you want, we will go through this, and if not, then we will leave it. So forward and reverse iterators over mutable sequences access values using an index. I think we should go for comparisons. So we will read through this comparison and then we will end this video. Let's go through comparison. Unlike C, all comparison operations in Python have the same priority, which is lower than that of any arithmetic, shifting, or bitwise operation. Also, unlike C, expressions like A less than B less than C have the interpretation that is conventional in mathematics. Comparisons yield Boolean values, true or false. Custom-rich comparison methods may return non-Boolean values. In this case, Python will call bool on such values in Boolean context. Comparisons can be chained arbitrarily. Example, x less than y less than equal to z is equivalent to x less than y and y less than equal to z, except that y is evaluated only once. We have seen this in the operators. We have seen this paragraph. Formally, if a, b, c up to y, z are expression and op1, op2, opn are comparison operators, then op1b, op2, c and so on y, op and z is equivalent to a op1b and b op2c and so on, except that each expression is evaluated at most once. Note that a op1b op2c does not imply any kind of comparison between a and c. So for example, x less than y greater than z is perfectly legal, though perhaps not pretty. We now look at value comparisons. The operators less than, greater than, equality, greater than, equal to, less than, equal to and not equal to compare the values of two objects. The objects do not need to have the same type. Now here it says the object do not need to have the same type, but if you see here, it says that the two sequences when compared must be of the same type. So there is a difference here in when we read this and when we read this. Okay, So for two sequences to be compared, they should have of the same type. But here it says to compare values of two objects using these operators, the objects do not need to have the same type. So this chapter states that the object have value in addition to type and identity. The value of an object is a rather abstract notion in Python. For example, there is no canonical access method for an object's value. Also, there is no requirement that the value of an object should be constructed in a particular way. Example, comprised of all its data attributes. Comparison operators implement a particular notion of what the value of an object is. One can think of them as defining the value of an object indirectly by means of their comparison implementation. Because all types are direct or indirect subtype of object, they inherit the default comparison behavior from object. Types can customize their comparison behavior by implementing rich comparison methods like less than, described in basic customization. We will go and look at basic customization also. The default behavior of equality comparison and not equal is based on the identity of the objects. Hence, equality comparison of instances with the same identity results in equality, and equality comparisons of instances with different identities result in inequality. A motivation for this default behavior is the desire that all objects should be reflexive. That is, x is y implies x is equal to y. A default order comparison less than, greater than, less than, equal to, greater than, is equal to is not provided. And an attempt raises type error. A motivation for this default behavior is the lack of similar invariant as for equality. The behavior of the default equality comparison, that instances with different identities are always unequal, may be in contrast to what type will need that have a sensible definition of object value and value based equality. Such types will need to customize their comparison behavior, and in fact a number of built-in types have done that. The following list describes the comparison behavior of most important built-in types. So this section is of very high interest for us because this is what we will need to deal with. So since we are discussing sequences, so you see that this is where it says sequences can be compared only within each of their types, with the restriction that ranges do not support order comparison. Equality comparison across these types result in equality, and ordering comparison across these types raises type error. Sequences compare lexicographically using comparison of corresponding elements. The built-in containers typically assume identical objects are equal to themselves. That lets them bypass equality tests for identical objects to improve performance and to maintain their internal invariance. So this is what is important for us, and for now we will go back to our discussion on what common sequence operations are. For other objects, we will go and visit comparisons time to time. So for example, we did not study objects, values and types. So you can go through this, okay, and understand. But remember that comparison typically means that you have overloaded that less than, equality, or such comparison operators. So when we are talking about these comparison operators, they are implemented using operator overloading in Python. So your custom type, how it defines these overloaded functions when you write a class, that will determine how the comparison will take place. That is the essence of this. You can define customization, like here we have seen this customization. So these customizations allow you to determine the behavior. For example, as you can see, these functions, overloaded operations, will determine the behavior of all the less than, greater than operations. These are called rich comparison methods. Coming back to our discussion on common sequence operations, forward and reverse iterators over mutable sequences access values using an index. That index will continue to march forward or backward even if underlying sequence is mutated. The iterator terminates only when an index error or stop iteration is encountered. Now there are some notes here. While the in and not in operations are used only for simple containment testing in the general case, Some specialized sequences such as string, bytes, byte array are also use them for subsequence testing. For example, GG in eggs returns you true. The values of n less than 0 are treated as 0, which yields an empty sequence of the same type as S. Note that, now be very careful about this line which I am going to read. Note that items in the sequence S are not copied. They are referenced multiple times. This often haunts new Python programmers. For example, if we run this, it will give us a list of 3 lists which are empty. But if you append 3 to the first one, it will get appended to each one of them because they are not copies of each other, but rather the same thing is referenced multiple times. So this list is one element list containing an empty list. So all 3 elements of this empty list into 3 are references to this single empty list. Modifying any of the elements of list modifies this single list. You can create a list of different lists this way. That is, you say list 0 dot append 3, list 1 dot append 5, list 2 dot append 7. And to create a list of different lists, you use list comprehension like this. You don't use repetition operator. Okay. If I or j is negative, when we talk about I and j, we are talking about this I and j. Okay. If I or j is negative, the index is relative to the end of sequence s len s plus I and len s plus j is substituted. But note that minus 0 is still 0. Slice. So what here it is talking about is the negative indices. Let me show you what does it mean. Suppose there is a list 1, 2, 3. Then the indexing goes like this: minus 3, and this will be minus 2, and this will be minus 1. So the index of 3 is minus 1, 2 will have minus 2, and 1 will have minus 3. That's how negative indexing works. The slice of S from I to J is defined as the sequence of items with index k such that I less than equal to k less than j. If I or j is greater than len s, use len s. If I is omitted or none, use 0. If j is omitted or none, use len s. If I is greater than or equal to j, the slice is empty. The slice of S from I to j with step k is defined as a sequence of items with index x is equal to I into I plus n into k such that 0 less than equal to n less than equal to j minus I by k. In other words, the indices are I plus k, I plus 2 into k, I plus 3 into k, and so on, stopping when j is reached but never including j. When k is positive, I and j are reduced to len s if they are greater. When k is negative, I and j are reduced to len s minus 1 if they are greater. If I or j are omitted to none, they become end values, which end depends on the sign of k. Note k cannot be 0. If k is none, it is treated like 1. Concatenating immutable sequences always result in a new object. This means that building up a sequence by repeating concatenation will have a quadratic runtime cost in the total sequence length. So what does it mean is, suppose you have a string, okay, and you are concatenating it. So the cost would be twice n, okay, because n, it will iterate the first object n times and the second object n times again. Okay, now if you concatenate with the third one, it will be 3n. So if you are concatenating n objects, the order will be on square. To get a linear runtime cost, you must switch to one of the alternatives below. If concatenating str objects, you can build a list and use str.join at the end, or else write to an io.string io instance and retrieve its value when complete. If concatenating bytes objects, you can similarly use bytes.join or io.bytes io, or you can do in place concatenation with a byte array object. Byte array objects are mutable and have an efficient over allocation mechanism. If concatenating tuple objects, extend the list instead. For other types, investigate the relevant class documentation. Some sequence types such as range only support item sequences that follow specific patterns and hence do not support sequence concatenation or repetition. Index raises value error when X is not found in X. This we are talking about item number 8, that is when you are getting the index of the first occurrence of X. So index raises a value error when X is not found in X. Not all implementations support passing the additional arguments I and J. These arguments allow efficient searching of subsections of the sequence. Passing the extra argument is roughly equivalent to using si::j dot index X without copying any data and with the return index being relative to the start of sequence rather than the start of the slice. So I think I'll stop here, and in the next video we will start looking at immutable sequence types and mutable sequence type. And so I think that we should end here. I hope that you have found this video useful and informative. Please like the video, share it as much as you can on social media, and let me know your thoughts in comment box. What do you think of these videos? And we will continue this. So there's quite a lot of documentation we have to go through. As you can see in the scroll bar, we are around at 20%. So it will be a while before we end the standard library. Please have patience, and we will eventually go through this. Thanks a lot for watching. Happy programming.